Okay, I'm back. So here, when you're looking for the summation of the first n terms of an arithmetic series, this is going to be the following. This equals a sub 1 plus a sub n, all of this times n over 2. I had to think about the derivation. So here, for example, if I wanted the summation of the first 14 terms, where I am given this definition of a sub n, that would equal the following. That would equal a sub 1 plus a sub n. What is a sub 1? 7 plus a sub n, or a sub 14, is negative 38. All of that times 14 over 2. And you can figure out what this number is. The point is, this number, though, is the summation of the first 14 terms. This is the 14th term, okay? I just realized I forgot to say here, this should be, comma, n is bigger than or equal to 1 for the domain, okay? So I should say this too, in terms of like derivation, like how on earth did I get these, and how on earth did I get these? We actually did derive these when you took TIC, TFA. I certainly can do that for you. Maybe I'll do a separate screencast for that, okay? Okay, here is the nth partial sum in summation notation. So the nth partial sum, I could, for an arithmetic series, okay, you have this. Now, what would be the nth partial sum using summation notation? Okay, well, let's see if you can follow me here. If I'm using summation notation, and I want to find the nth partial sum in summation notation for an arithmetic series, well, let's see. That would be the summation, okay? And this notation is saying the sum of the first n terms, right? So that means I would like to say, okay, the summation from, let's say I want to say k equals 1, and I want to end at n. So what's critical here is I want the number of terms I'm adding to correspond to that letter right here. This is the nth partial sum. This letter, dealer's choice, okay? So my statement to you about the fact that you will have, letters thrown everywhere. Textbooks use different letters. You've got to know what the letter stands for in each question, okay? Well, let's take a look. What am I plugging this K into? Well, I want the summed here to stand for, to be this, okay? Now, many of you would go ahead and do this. Many would say, okay, I want the summed here to be a sub 1 plus d times n minus 1, because you're blindly just kind of dropping in this expression for the nth term of an arithmetic series. But look at your letters. Here, n is standing in for the kind of quote-unquote the last term that you're adding up, right? And what is changing integrally is k. So you tell me what should change in this summed. Very good. What should change here is this n should be a k, because k is the thing that is changing as an integer from 1 to n. Okay? So this right here, interestingly, if you look at this describes the same thing as this, but in a different form. And this kind of goes to what I was saying in class. There are some types of series that lend themselves, or that associate with a nice formula for a sum, but not all of them. Okay, arithmetic and geometric series are one of those. So if you want to write this sum here, the example I gave, right, with this particular sum, where each term is described as thus, in this case, we could say the summation from k equals 1 to, let's say here I just want to talk about the 14th partial sum. That means the upper number is 14, and let's see, there it is, 7 minus 3 times k minus 1. Okay, and there is my specific sum here for this particular example, and here's a general summation notation expression for an arithmetic series. And then down here, look what this is. This is the summation of the first infinite number of terms. So for an arithmetic series, well, what's that going to be? This is just going to equal the summation from k equals 1 to infinity of a sub 1 plus d times k minus 1, okay? It's just an infinite arithmetic series. It's an arithmetic series with infinite number of terms. If I were to use this particular example right here, and I wanted to say, I don't want to discuss the 14th partial sum, I want to express the infinitieth partial sum, if you will. This would become then positive infinity, okay? Now, let me ask you this. When it comes to infinite arithmetic series, okay? Infinite arithmetic series. Do infinite arithmetic series converge or diverge? When you are talking about, ladies and gentlemen, be very careful. When you're talking about whether a sum converges or diverges, you want to ask yourself, okay, if I add up these infinite terms, will my sum converge or diverge? Now, some of you may be looking in the mirror and you say to yourself, well, what is she talking about? If you're forever adding something, which is what you would be doing in an infinite arithmetic series case, and don't forget, adding something is the same thing as subtracting something, right? If you're forever adding something, whether that something is a positive or a negative quantity, if you're always adding something, won't that sum have to diverge? Because if you're forever adding something, the sum is going to approach either positive infinity or negative infinity. Now, maybe some of you smart Alex will say, well, what if you're adding 0 forever? And, well, I'm going to tell you this. If you're adding 0 forever, we're going to call it as it is. Adding 0 means you're not adding anything, okay? But the truth of the matter is that infinite arithmetic series always diverge, because you are always forever adding and subtracting something, okay? Forever. So an infinite arithmetic series always, by definition, has to diverge, okay? Now, geometric series, let's talk about these. A geometric series, let's take a look, okay? I could write the same thing here. Series with a constant, that's a constant, not difference. The series for a geometric series, there's a constant ratio. Okay, it's a constant ratio between terms. And oftentimes that constant ratio is referred to as R. And make sure we all agree, the constant ratio is a sub n plus 1 over a sub n. So make sure you take the latter term divided by the smaller term. Let me give you some examples of a geometric series. 1 plus 2. Whoa, did you see that? I said 1, but my hand said 2. That's so funny. 1 plus 2 plus 4 plus 8 plus 16 plus so on and so forth, okay? The constant ratio here is positive 2. Another example of a geometric series would be, let's take a look, 9 minus a third plus 1/9 minus 1/27 plus 1/81, ... Here, the constant ratio is negative 1/3. Okay, negative 1/3 is the constant ratio. All right. Let's go through here. When it comes to geometric and arithmetic series, we have these nice definitions. A definition for the a sub nth term of a geometric series is the following. It's a sub 1 times r to the n minus 1. Okay, so that is my formula for the nth term of a geometric series. So if, for example, I had this series, let's talk about this series right here. And I wanted to describe or generate a formula that would give me, say, the 4th term of the series or the 21st term of the series. Well, I could use, okay, I could take this over here. I'm going to say, okay, this is defined by a sub n equals a sub 1 means the first term, 9 times negative 1/3 to the n minus 1. And then I just did it again like I did before. Here again, the domain is n is bigger than or equal to 1. So my example here would also be n is bigger than or equal to 1. Okay? This expression right here gives us, this is a formula for the nth term of this series. Okay? So I could, if I wanted to, I could say, let's find the 21st term of that series. Now, I'm not going to actually do this out. Maybe you will. But if I wanted to find the 21st term of the series, I'd have to, compute this number. That would give me the 21st term. A sub n should not be confused with S of n. S of n means the same thing as it did before. This is the nth partial sum. Okay, it's the nth partial sum of a geometric series. Okay, and we have a nice formula for that. This equals a sub 1 times 1 minus r all over 1 minus r to the n. Okay, this is your nth partial sum. This is your nth partial sum. So once again, let's say in the example above, let's use this little green series here. Let's say I wanted to find the summation of the first 10 terms of that series. Well, that's going to equal a sub 1, which is 9, times 1 minus, r is negative 1/3. So 1 minus negative 1/3, watch that double negative, all divided by 1 minus negative 1/3 all to the 10th, okay? Now again, you can use your calculator here. I'm not going to because I've got some, this is kind of an ugly, gross number. But at the end of the day, this is going to equal some number. But that number here is, again, it's the sum of the first 10 terms, okay? Once again, I want to make sure you understand that I am not pulling these things out of just the sky. There's a very nice and they're very neat derivations for those. Okay, let's just finish this up here. S of n in summation notation. S of n in summation notation, well, what would that be? In summation notation, this is the summation of, okay, and I'm going to watch my letters here, k equals 1 to n. Again, this n has to correspond to this n because this is the sum of the first n terms. Now, the sum end is going to be the expression for the nth term. So this is going to be a sub 1 times r to the n minus 1. There is my nth partial sum in summation notation. If I want to use this particular example, I could say, I can take this, okay, and I can say, how do I describe the 10th partial sum using summation notation? I'm going to need to see this, won't I? Okay, so this is going to become, and watch our k's and n's, the summation from k equals 1 to n of 9 times negative 1/3 to the power of k minus 1. Okay, so that's my particular example here. And then just like before, okay, the summation of infinite terms in a geometric series, the only change here would be this, summation from k equals 1 to positive infinity of a sub 1 times r to the n minus 1. Whoa. I just caught, this should be a k. Holy gadzooks, and this should be a k. Okay. All right. And I'm going to leave you an infinite geometric series. Okay, infinite geometric series. infinite geometric series, do they converge or diverge? And let me say this, infinite geometric series, they converge if R is between, oh my stars and stripes, is between those two values. R has to be between -1 and 1. R can't equal -1 or 1. R has to be between -1 and 1. If in an infinite geometric series, R is not in this range, then the series will diverge. Okay? I'm going to answer this question when I see you next. Here's a couple of things, everybody. Your homework tonight. If anywhere in your homework a question refers to something called the divergence test, please ignore it. We haven't covered it yet. The other thing I wanted to share with you is I just noticed this. Your textbook, it uses what's called brace notation to describe sequences. In other words, it'll have something like this. Okay? For us, everybody, this means the same thing as A sub n equals 3n, where n is bigger than or equal to 1, okay? And you want to stop at 7 up here. So that means the sequence is going to be A sub 1 is 3, 6, 9, 12, all the way through. The last term is going to be 21, okay? So just be mindful of that.